Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Take a moment to settle in, let your body sink into wherever you're resting, and know that for the next couple of hours, there's nowhere else you need to be. Where in the world are you watching from? A quiet bedroom where the day has finally released its hold? A cosy corner where the stars might be visible through your window? Wherever you are, you're in the right place. Tonight, we're going to explore something that sounds like science fiction but is absolutely verifiably real. We live inside a cosmic void, an enormous bubble of relative emptiness in the universe, nearly 1 billion light years across. It's called the KBC Void, named after the astronomers who identified it, and it's one of the largest structures ever discovered in the cosmos. We'll learn how scientists found this vast emptiness, what it means for our understanding of the universe, and why living in such a place might actually explain some of the biggest mysteries in cosmology. It's a journey that spans the entire observable universe and challenges everything we thought we knew about our place in the cosmic landscape. But don't worry. This isn't going to be an alarming revelation about cosmic doom or existential crisis. Instead, we'll move slowly and carefully through the evidence, the history of the discovery, and the beautiful implications of residing in such an unusual cosmic neighbourhood. By the end, I think you'll find there's something oddly comforting about understanding the true nature of our cosmic address. If you enjoy these calm explorations of the universe, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for returning to these slow drifts through space and time. So settle in. Let your shoulders drop away from your ears, take a slow breath, and feel it fill your lungs completely before releasing. And let's begin our slow drift through the largest void in the known universe. There's nowhere you need to be right now, nothing you need to do, just listen, and let the story of our cosmic neighbourhood unfold around you, like the darkness of space itself. Before we can understand what it means to live inside a cosmic void, we need to reconsider what we mean by nothing. In everyday life, we think of nothing as the complete absence of anything, a true emptiness. But in cosmology, nothing is rarely so simple. When astronomers speak of voids in space, they're not describing regions where absolutely nothing exists. Instead, they're identifying areas where significantly less exists than expected, places where the density of matter falls far below the cosmic average. Think of it like this. If the universe were an ocean, voids would be the places where the water is still present but noticeably thinner, where you could swim more easily through reduced resistance. The universe, as we observe it today, is not distributed evenly. Matter clumps together in an intricate cosmic web, forming galaxies, galaxy clusters, and enormous superclusters connected by filaments of dark matter and gas. Between these dense structures lie the voids, vast regions spanning hundreds of millions of light years where galaxies are rare, where the normal density of matter drops to perhaps 10 or 20% of the universal average. These voids aren't perfectly empty. A few small galaxies might drift through them, isolated and distant from their cosmic neighbours. But compared to the rich tapestry of galaxies clustered along the cosmic web's filaments, voids represent a profound scarcity. What makes cosmic voids fascinating is their size and prevalence. They're not small pockets of emptiness scattered here and there. Voids actually make up the majority of the universe's volume, perhaps as much as 80%. The cosmos is more empty than full, more void than solid, more absence than presence. Galaxies and their associated dark matter occupy the walls, filaments and nodes of the cosmic web, while voids form the interior spaces, the chambers and halls of this vast cosmic architecture. It's a structure that emerged from the earliest moments after the Big Bang, when tiny fluctuations in density began to grow under gravity's patient influence. These fluctuations started impossibly small, quantum variations in the density of matter and energy, when the universe was younger than a second old. Over billions of years, gravity amplified these differences. Denser regions attracted more matter, growing denser still, while less dense regions saw their material pulled away toward the growing concentrations. The rich grew richer, and the poor grew poorer, creating an increasingly stark division between the crowded and the empty. By the time the universe was a few billion years old, this process had created the cosmic web we observe today, a foam-like structure of dense filaments surrounding vast voids. Scientists discovered this structure gradually through painstaking surveys of galaxy positions. In the 1970s and 80s, astronomers began mapping the three-dimensional distribution of galaxies, measuring not just their positions on the sky, but their distances from Earth. What they found surprised them. Galaxies weren't scattered randomly through space as many had assumed. Instead, they formed clear patterns, sheets and filaments with enormous gaps between them. The first major void discovered was the Butter's Void, identified in 1981. A region roughly 300 million light-years across containing remarkably few galaxies. It was nicknamed the _1_, and its discovery forced astronomers to reconsider their models of cosmic structure. The realization that voids are fundamental to cosmic architecture changed how we think about the universe. We don't live in a uniform sea of galaxies. We live in a universe that's mostly empty, where matter gathers in thin walls and filaments like soap bubbles, surfaces, with vast empty chambers inside. This structure tells us about the universe's history, about the nature of dark matter and dark energy, about how gravity and expansion have competed over cosmic time. And understanding voids helps us understand something even more profound. Our own cosmic neighbourhood might be unusual in ways we're only beginning to appreciate. Which brings us to a question worth contemplating. If the universe is filled with voids and we can observe them all around us, could we ourselves be inside one? Could our home, the Milky Way galaxy, reside not in the dense cosmic web but in one of these underpopulated regions? The answer to that question has profound implications for everything we think we know about the universe's expansion. To understand why living in a void matters, we need to explore one of the most vexing problems in modern cosmology, the Hubble tension. It's a disagreement that sounds technical but cuts to the heart of how we measure the universe itself. The Hubble constant describes how fast the universe is expanding, and for decades scientists have used two different methods to measure it. The problem is these methods give different answers, and the gap between them refuses to close. The first method looks at the cosmic microwave background, the ancient light released when the universe was just 380,000 years old. This primordial radiation carries within it the imprint of the universe's composition and expansion rate in those early moments. Satellites like the Planck Observatory have measured this light with extraordinary precision, allowing cosmologists to calculate what the Hubble constant should be today, based on our understanding of cosmic evolution. This method gives a value of about 67 kilometers per second per megaparsec. What this means is that for every megaparsec, roughly 3.3 million light-years of distance, space expands by 67 kilometers per second. Galaxies farther away recede faster because there's more expanding space between us and them. The second method uses what astronomers call the cosmic distance ladder, a series of measurement techniques that build upon each other to reach greater and greater distances. The process begins with measuring distances to nearby stars using parallax, the apparent shift in their position as Earth orbits the Sun. Once we know these nearby distances precisely, we can calibrate the brightness of certain standard candles, stars whose intrinsic luminosity we understand. Cepheid variable stars, which pulse with a period directly related to their brightness, serve as crucial rungs in this ladder. By measuring their apparent brightness, we can calculate their distance. Using Cepheids, astronomers can measure distances to nearby galaxies, and within those galaxies, they can observe supernovae, stellar explosions that briefly outshine entire galaxies. Type 1. A supernovae, in particular, have remarkably consistent peak brightness, making them excellent distance markers. By comparing their observed brightness to their known intrinsic luminosity, astronomers can calculate distances to galaxies hundreds of millions of light-years away. And by measuring the redshift of those distant galaxies, the stretching of their light caused by cosmic expansion, scientists can determine how fast the universe is expanding. This method, refined over decades and recently improved by the Hubble Space Telescope, gives a Hubble constant value of about 73 kilometers per second per megaparsec. The difference between 67 and 73 might not sound significant, but in cosmology, it's enormous. It's far larger than the uncertainties in either measurement, and it's persisted even as both methods have been refined and improved. This is the Hubble tension, and it's been described as either a profound mystery or the first crack in our cosmological model. If both measurements are correct, something fundamental about our understanding of the universe must be wrong. Perhaps dark energy behaves differently than we think. Perhaps the cosmic microwave background doesn't tell us what we believe it does. Or perhaps the local universe, the region within 1 billion light-years of us, is somehow different from the universe at large. This last possibility is where voids enter the picture. The cosmic distance ladder measures the expansion rate in our cosmic neighbourhood within 1 billion light-years or so. The cosmic microwave background, by contrast, tells us about the universe on the larger scales, averaged over the entire observable cosmos. If our neighbourhood is unusual, if we live in a region where the density of matter is lower than average, then the local expansion rate might genuinely differ from the global average. Space might expand slightly faster in underdense regions, where there's less gravitational pull to slow the expansion. If we live in a significant void, that could explain why local measurements give a higher Hubble constant. For years, this possibility was considered and largely dismissed. Early measurements suggested the local universe wasn't particularly unusual, but as surveys improved and extended to greater distances, a different picture began to emerge. Perhaps our cosmic neighbourhood is more unusual than we thought. Perhaps we do live in a void, and perhaps that void is larger and more underdense than almost any other known void in the observable universe. This realization didn't come suddenly. It emerged gradually from careful observations and statistical analysis, from the slow accumulation of evidence that something about our corner of the cosmos wasn't quite average. And this gradual recognition leads us to the astronomers who first identified and measured this enormous empty region that we call home. The void we inhabit wasn't discovered through a single dramatic observation. Instead, it emerged from careful statistical analysis of galaxy surveys, from comparing the density of galaxies in our neighbourhood to the density expected in an average region of space. The work was led by Ryan Keenan, Amy Barger, and Lennox Cowie, 3 astronomers whose initials gave the void its name, the KBC Void. Their research, published in 2013, presented evidence that the Milky Way resides in a significantly underdense region of space, a void extending roughly 1 billion light-years across. To understand how they made this discovery, we need to appreciate the challenge of mapping our cosmic neighbourhood. When we look out at the universe, we see galaxies in all directions, scattered across the sky like stars visible on a clear night. But to determine whether we're in a void, we need to know not just where galaxies appear on the sky, but how far away they are and how their density changes with distance. We need a 3-dimensional map, and creating such a map requires measuring the distance to thousands upon thousands of galaxies. Astronomers measure these distances primarily through redshift, the stretching of light caused by cosmic expansion. As the universe expands, the space between galaxies stretches, and this stretching affects the light travelling through that space. Light waves get stretched to longer, redder wavelengths, and the amount of stretching tells us how much the universe has expanded since the light began its journey. For relatively nearby galaxies, this relationship between redshift and distance is straightforward. The farther a galaxy is, the more its light has been stretched, and by measuring that stretching precisely, we can calculate the galaxy's distance. Keenan and his colleagues used existing galaxy surveys, catalogues containing the positions and redshifts of tens of thousands of galaxies. They analysed how galaxy density changed as a function of distance from the Milky Way, looking for deviations from the expected average. What they found was striking. The density of galaxies in our local region, out to about 1.5 billion light-years, was significantly lower than the cosmic average. Not just slightly lower, but reduced by perhaps 30 to 40% compared to what would be expected in a typical region of space. This underdensity wasn't uniform with distance. The void appeared to have a structure, a profile. Near the centre, roughly where we are, the density was lowest. As you moved outward, the density gradually increased, reaching approximately average values at the void's edge, about 1 billion light-years away. This profile is characteristic of voids in the cosmic web. They're not sharp-edged bubbles, but gradual depressions in density, regions where matter is present but substantially thinned out compared to the universe at large. The size of the KBC Void was remarkable. At roughly 1 billion light-years across, it would be one of the largest voids ever identified. Most known voids span a few hundred million light-years at most. The Boötes Void, the first major void discovered, is about 300 million light-years across. The KBC Void dwarfs it, encompassing thousands of smaller voids and underdense regions in a single enormous depression in the cosmic density field. If confirmed, it would represent a significant departure from cosmic homogeneity on scales approaching the limits of what's theoretically possible given our understanding of cosmic structure formation. The discovery was met with both interest and skepticism. Some astronomers questioned whether the statistical methods used were robust, whether the galaxy surveys employed were complete enough to draw such strong conclusions. Others pointed out that previous analyses hadn't detected such a significant underdensity. The debate highlighted a fundamental challenge in observational cosmology. We have only one vantage point, one position from which to observe the universe. We can't step outside and look at our neighbourhood from afar. We can only analyse what we see from here and carefully compare it to expectations. Further research followed. Other groups used different galaxy surveys and different statistical techniques to test the claim. Some studies supported the existence of a significant local underdensity. Others suggested the effect was smaller or less certain than initially claimed. The exact size and depth of the void became a matter of ongoing research and refinement. But the basic finding persisted. Our cosmic neighbourhood appears to be less dense than average, and this underdensity extends to distances of several hundred million light-years at minimum, possibly reaching out to 1 billion light-years or more. What made the KBC Void particularly significant wasn't just its size, but its potential to explain the Hubble tension. If we live in such a large, underdense region, the expansion rate measured locally might genuinely differ from the global average, potentially reconciling the conflicting measurements that have troubled cosmologists for years. This possibility transforms the void from a curious local feature into a potential key to unlocking one of cosmology's deepest mysteries. The connection between living in a void and the Hubble tension rests on a subtle but important aspect of general relativity. Space doesn't expand at a single uniform rate everywhere. Instead, the expansion rate can vary slightly depending on the local density of matter and energy. In regions where matter is denser than average, gravity pulls inward more strongly, slowing the expansion slightly. In regions where matter is less dense, the gravitational pull is weaker, and expansion can proceed slightly faster. This variation is generally small, but over distances of hundreds of millions of light-years, it can become measurable. Think of the universe's expansion like the rising of bread dough. The dough expands overall, but individual regions might rise at slightly different rates, depending on their composition and the local conditions. A pocket with more yeast might rise faster. A denser region might rise more slowly. The universe works similarly. The overall expansion, driven by dark energy and the energy density of the cosmos, proceeds at an average rate. But local variations in matter density create local variations in the expansion rate. Inside a void, where matter density is lower than average, the expansion can be slightly faster. There's less mass pulling back against the expansion, less gravitational resistance to the stretching of space. This effect is most pronounced at the void's centre and diminishes as you approach the denser walls at the void's edge. For an observer inside a void, particularly near the centre, measurements of the local expansion rate might yield higher values than measurements of the global average expansion rate derived from the cosmic microwave background. The mathematics of this effect were worked out in detail by theorists exploring various cosmological models. They calculated how much the expansion rate could differ between the interior of a void and the universe at large. The results showed that for a void to significantly affect local Hubble constant measurements, it would need to be both large and substantially underdense. A small void or a weakly underdense region wouldn't create enough of an effect, but a void like the KBC Void, roughly 1 billion light-years across with a density deficit of 30 to 40%, could potentially create a discrepancy in the Hubble constant of several kilometers per second per megaparsec. This is tantalizingly close to the observed Hubble tension. Recall that the local measurements give about 73 while the cosmic microwave background predicts 67. The difference of about 6 units could potentially be explained if we're measuring the expansion rate from inside a large void. However, the exact numbers depend on details like the void's precise density profile, its size, and where exactly we sit within it. Some models suggest the void could fully explain the tension. Others suggest it could account for part but not all of the discrepancy. There's another layer to consider. If we're inside a void, then when we use the cosmic distance ladder to measure the Hubble constant, we're primarily sampling galaxies within the void or just beyond its edge. These galaxies are receding from us through space that's expanding slightly faster than the cosmic average. Our local measurements would naturally give a higher Hubble constant because we're measuring a locally enhanced expansion rate, not the global average. Meanwhile, the cosmic microwave background measurements average over the entire observable universe, including both voids and overdense regions, and thus give us the true global average. This scenario is elegant because it doesn't require new physics. We don't need to modify our theories of dark energy or gravity. We don't need to imagine that the cosmic microwave background is misleading us about the early universe. We simply need to acknowledge that our local cosmic neighbourhood is unusual, and that our measurements naturally reflect local conditions rather than global averages. It's a humbling thought in some ways. We've grown accustomed to thinking that the universe looks roughly the same everywhere, that our location is unremarkable. The cosmological principle, a guiding assumption in modern cosmology, states that the universe is homogeneous and isotropic on large scales. But if we live in a void, we're acknowledging that our local environment is somewhat special, even if the void itself formed through completely ordinary processes. Testing this hypothesis requires careful work. We need better measurements of galaxy density at various distances, extending far beyond the void's presumed edge to confirm whether density returns to average. We need more precise measurements of the local expansion rate, using multiple independent methods to ensure we're not being misled by systematic errors. And we need sophisticated simulations of cosmic structure formation to determine whether a void as large as the KBC Void is consistent with our understanding of how the universe evolved. These investigations continue, each refining our picture of our cosmic address and its implications for the Hubble tension. One of the most challenging aspects of the KBC Void hypothesis is a question of probability. If we live in one of the largest and deepest voids in the observable universe, how likely is that? Should we be suspicious when we find ourselves in such an unusual location? This question touches on a deep issue in cosmology known as the Copernican principle. The idea that we should not assume we occupy a special or privileged position in the universe. Historically, the Copernican principle has served science well. Copernicus himself argued that Earth is not the centre of the universe, but merely one planet orbiting the Sun. Later, astronomers showed that the Sun is not the centre of the galaxy, but an ordinary star in the galaxy's outer regions. The Milky Way, we discovered, is one of billions of galaxies scattered through space with no particular distinction. Each step has reinforced the idea that there's nothing special about our location. We're not central, not unique, not privileged. We're typical. But typical doesn't mean we must be exactly average in every way. In a universe large enough and varied enough, some observers will inevitably find themselves in unusual locations simply by chance. The question is whether the KBC Void is so unusual that we should doubt its existence rather than accept that we happen to live there. Statisticians and cosmologists have tried to quantify this by calculating what fraction of the universe's volume is occupied by voids as large and underdense as the KBC Void. The calculations depend on our models of cosmic structure formation, using simulations that evolve the distribution of matter from the early universe to the present day. Researchers can identify all the voids that form and measure their sizes and density profiles. They can then count how many voids similar to the KBC Void appear in a representative volume of space. The results vary depending on the simulation details, but generally voids as large as the KBC Void are rare, but not impossibly so. Perhaps 1% of the universe's volume, or maybe as much as 5%, might be occupied by voids of comparable size and underdensity. This means that while we'd be somewhat unlucky to find ourselves in such a void, it's not astronomically improbable. In a universe with countless galaxies and countless observers, many would live in large voids simply by chance. We might be among them. However, if future observations show the void is even larger or deeper than current estimates suggest, the probability decreases, and we'd have more reason to question whether we're interpreting the data correctly. There's also the question of observational bias. We can only measure the properties of our local universe from our position within it. If different observers in different locations measured their local Hubble constant, they get slightly different values depending on their local density environment. Most would measure values close to the global average because most of space is close to average density. But some would measure higher values if they're in voids, and some would measure lower values if they're in overdense regions. The fact that we measure a particular value doesn't tell us we're in a special place. It tells us about our local environment, and our task is to determine whether that environment is consistent with what we'd expect in a typical large-scale structure. The philosophical dimension of this question is subtle. If we accept that we live in a large void, are we abandoning the Copernican principle? Not necessarily. The principle doesn't require that our location be average in every measurable way. It requires that the laws of physics are the same everywhere, and that the universe doesn't have a special centre or edge. A large void is a natural consequence of structure formation, predicted by the same physics that creates galaxy clusters and filaments. Living in one doesn't mean we're cosmically privileged. It means we happen to reside in one of the universe's many underdense regions. Moreover, the KBC Void, if it exists, isn't unique. Other large voids have been identified in distant parts of the universe. Some are comparable in size, though possibly not as deep in their underdensity. We may simply be the observers inside one of many similar structures, and observers in those other voids might be having similar debates about whether their neighbourhoods are unusually empty. What's crucial is that we test the hypothesis rigorously. We need to determine whether the evidence genuinely supports a void of the proposed size and depth, or whether other explanations fit the data better. We need to check whether the void's properties, if confirmed, can actually explain the Hubble tension quantitatively, and we need to consider alternative explanations for the tension that don't require us to live in an unusual location. This careful balance between accepting the data and questioning our assumptions is the heart of scientific cosmology. We follow the evidence wherever it leads, but we remain cautious, aware that our position within the universe might influence what we see and how we interpret it. And as we contemplate our possible residence in an enormous cosmic void, we begin to wonder what else this unusual neighbourhood might teach us about the universe. The story of how we discovered the KBC Void is inseparable from the story of galaxy surveys, the massive observational programs that have mapped the three-dimensional distribution of galaxies across billions of light years. These surveys represent some of the most ambitious projects in observational astronomy, requiring decades of telescope time, sophisticated instruments, and careful data analysis. Without them, we would have no way to know whether we live in a void or in an average region of space. The first major three-dimensional galaxy survey was the Harvard-Smithsonian Center for Astrophysics Redshift Survey, often called simply the CFA survey, begun in the late 1970s. Astronomers measured the redshifts of thousands of galaxies, painstakingly determining their distances one by one. When they plotted the results in 3 dimensions, the cosmic web structure became apparent for the first time. Galaxies, before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. Galaxies weren't scattered randomly, but arranged in sheets and filaments with large gaps between them. This was a revelation, showing that the universe had far more structure than previously imagined. Subsequent surveys expanded this work dramatically. The 2-degree field galaxy redshift survey, conducted in the late 1990s and early 2000s, measured redshifts for over 200,000 galaxies. The Sloan Digital Sky Survey, or SDSS, which began in 2000, has measured spectra for millions of galaxies and continues to this day with successive generations of instruments and scientific goals. These surveys have created detailed maps of cosmic structure extending out billions of light years from Earth, revealing the cosmic web in unprecedented detail. Each survey uses similar techniques. Astronomers select galaxies visible in a particular region of sky, then use spectrographs to measure the precise wavelength of light from each galaxy. By comparing the observed wavelengths to the known wavelengths of features in galaxy spectra, they can determine how much the light has been redshifted by cosmic expansion. This redshift translates to a distance, allowing each galaxy to be placed in 3-dimensional space. When thousands or millions of galaxies are mapped this way, the large-scale structure emerges naturally from the data. Identifying voids within this structure requires statistical analysis. Astronomers divide space into cells and count how many galaxies fall within each cell. Regions with significantly fewer galaxies than expected represent voids. The challenge is distinguishing genuine large-scale voids from random fluctuations in galaxy counts, or from observational artifacts like regions of the sky obscured by dust in our own galaxy. Sophisticated algorithms help identify coherent underdense regions, separating true voids from noise. For the KBC Void specifically, multiple surveys contributed to its identification and characterization. The SDSS provided detailed maps of galaxy positions in certain regions of sky. The 2-micron all-sky survey, or 2MASS, which mapped galaxies in infrared light, helped fill in regions obscured in optical surveys. The 6th data release of the SDSS Galaxy Survey, or 6DFGS, measured redshifts for galaxies primarily in the southern sky. By combining data from these various sources, astronomers could create a more complete picture of galaxy density in our local cosmic volume. The process of confirming the void's existence involves comparing observed galaxy counts to theoretical predictions. Cosmologists use simulations of cosmic structure formation to predict how many galaxies of various types should appear in a random volume of space. They then compare these predictions to what's actually observed in our neighbourhood. A significant deficit indicates an underdensity. The depth of the void, how underdense it is, can be quantified by calculating the ratio of observed to expected galaxy density. For the KBC Void, this ratio is estimated at around 60 to 70%, meaning the local region contains only 60 to 70% of the galaxies expected in an average region of similar size. Measuring the void's size requires tracking how galaxy density changes with distance in all directions from the Milky Way. This is more challenging because it requires surveys that cover the entire sky and reach sufficient depth in distance. Many early surveys focused on particular regions of sky, leaving gaps in coverage. Only with more recent comprehensive surveys have astronomers been able to trace the void's extent in all directions, confirming that it's not just a local fluctuation in one direction, but a coherent three-dimensional structure surrounding us. The ongoing nature of galaxy surveys means our understanding of the void continues to improve. Each new survey adds more galaxies, extends to greater distances, or covers previously unmapped regions of sky. These additions refine the void's density profile, adjust its estimated size, and increase our confidence that what we're seeing is real rather than an artifact of incomplete data. The work is painstaking and incremental, building certainty gradually through accumulation of evidence rather than dramatic single observations. And as these surveys extend farther into space, they reveal that the KBC Void, while unusual, exists within a larger context of cosmic structure that helps us understand how such a feature could form and what it means for the universe as a whole. To truly appreciate the KBC Void, we need to understand the cosmic web, the grand structure within which voids are embedded. The cosmic web is perhaps the most spectacular feature of the universe on large scales, a vast network of filaments, walls, clusters, and voids extending across the entire observable cosmos. It's a structure that began forming in the earliest moments after the Big Bang, and continues to evolve today under the patient influence of gravity and cosmic expansion. Imagine, if you will, a three-dimensional foam. The soap bubbles form walls and edges where the soap is concentrated, while the interior of each bubble is mostly empty air. The cosmic web has a similar structure. Galaxies cluster along filaments and walls, dense structures where dark matter and ordinary matter have accumulated over billions of years. These filaments connect massive clusters of galaxies, the nodes where the cosmic web is densest. Between the filaments lie the voids, vast empty regions that occupy most of the volume of space but contain only a small fraction of its matter. This structure formed from tiny density fluctuations in the early universe. When the universe was very young, shortly after the Big Bang, it was remarkably smooth and uniform, but quantum fluctuations during the inflationary epoch, a brief period of exponential expansion in the universe's first fraction of a second, created tiny variations in density. These variations were incredibly small, differences of only 1 part in 100,000, but they were enough. As the universe expanded and cooled, gravity began amplifying these tiny differences. Regions that were slightly denser than average had a slightly stronger gravitational pull. This pull attracted nearby matter, making these regions denser still. As they grew denser, their gravitational pull increased further, attracting matter from even greater distances. This process, called gravitational instability, created a runaway effect where the dense regions grew rapidly denser, while the underdense regions grew more empty as their matter was pulled away. Over hundreds of millions of years, this process transformed the nearly uniform early universe into the cosmic web we observe today. Dark matter played a crucial role in this process. Making up about 85% of all matter in the universe, dark matter interacts only through gravity. It doesn't emit, absorb, or reflect light, making it invisible to telescopes, but its gravitational influence is profound. Dark matter began clustering earlier than ordinary matter because it wasn't affected by radiation pressure that initially kept ordinary matter smooth. Dark matter formed the gravitational scaffolding of the cosmic web, and ordinary matter followed, falling into the dark matter's gravitational wells and eventually forming stars and galaxies. The filaments of the cosmic web are vast rivers of matter, streams of galaxies flowing along dark matter highways that can stretch hundreds of millions of light years. These filaments typically contain more galaxies than average, perhaps 2 or 3 times the cosmic mean density. Where filaments intersect, and they form clusters, massive collections of hundreds or thousands of galaxies bound together by gravity. The largest clusters contain tens of thousands of galaxies and can measure tens of millions of light years across. Between these dense structures lie the voids. Voids are not perfectly spherical bubbles, but irregular regions shaped by the surrounding filaments and walls. They expand as the universe expands, but they expand faster than the average expansion rate because they have less matter to gravitationally resist the expansion. Over time, voids grow larger as matter continues to drain out of them toward the denser regions. A process sometimes called void evacuation. A void that was moderately underdense a few billion years ago becomes more underdense over time as cosmic evolution continues. The typical void in the cosmic web measures between 100 and 300 million light-years across. Larger voids are rarer, and the largest known voids approach 500 million light-years in diameter. These supervoids are fascinating structures, representing significant departures from the average density. The KBC Void, if its size is confirmed at close to 1 billion light-years, would be among the very largest voids known, sitting at the extreme end of the size distribution. What determines void size? Primarily it's the scale of the initial density fluctuations that seeded cosmic structure. Larger initial fluctuations create larger final structures, but there are limits. The universe is only about 13.8 billion years old, and gravity takes time to create structure. There hasn't been enough time since the Big Bang for arbitrary large structures to form. The largest voids we observe are close to the maximum size predicted by our understanding of cosmic evolution, given the age and properties of the universe. This cosmic web structure is not static. It continues to evolve as the universe expands and ages. Filaments grow thicker as galaxies continue forming within them. Clusters grow more massive as they accrete galaxies from their surroundings. Voids grow emptier and larger as expansion continues. In the far future, as dark energy drives the universe's expansion to accelerate ever faster, the cosmic web will become increasingly sparse. Filaments will thin, clusters will spread apart, and voids will dominate even more of the cosmic volume than they do today. Understanding this structure helps us put the KBC Void in context. It's not a random anomaly, but a natural feature of cosmic evolution, formed by the same processes that created every other void in the universe, simply scaled up to an unusual size. And recognizing that we're part of this grand cosmic web, even if we're in one of its emptier regions, connects us to the entire history of the universe, from the first quantum fluctuations to the present day. When we discuss voids and the cosmic web, we're primarily talking about the distribution of galaxies, the visible structures we can observe with telescopes. But the cosmic web's true architecture is defined by dark matter, the mysterious substance that outweighs ordinary matter by a factor of 5 to 1, yet remains invisible to all our instruments except through its gravitational effects. Understanding the KBC Void requires understanding dark matter's role in creating and maintaining cosmic structure. Dark matter is one of the great discoveries of 20th century astronomy, though it was recognized reluctantly and only after decades of accumulating evidence. Astronomers first noticed something was wrong in the 1930s when Fritz Zwicky studied the Coma cluster of galaxies. He measured how fast galaxies within the cluster were moving and applied the virial theorem, a relationship between the motion of objects and the gravitational field they're experiencing. The result was shocking. The galaxies were moving so fast that they should have escaped the cluster's gravity long ago, unless there was far more mass holding them together than could be accounted for by visible stars and gas. Zwicky proposed that the cluster must contain vast amounts of unseen matter, which he called dark matter. For decades, this finding was largely ignored or explained away, but in the 1970s, Vera Rubin and her colleagues conducted detailed studies of galaxy rotation curves, measuring how fast stars and gas orbit at various distances from the centres of spiral galaxies. They found that stars far from the galactic centre were orbiting just as fast as those closer in, contrary to what would be expected if only visible matter were present. This implied that galaxies were embedded in large halos of dark matter, extending far beyond their visible disks. The evidence became overwhelming. Dark matter wasn't just present in clusters but in individual galaxies, and it outweighed ordinary matter significantly. Since then, multiple independent lines of evidence have confirmed dark matter's existence and measured its abundance. Observations of the cosmic microwave background show the effects of dark matter in the early universe. Gravitational lensing, the bending of light by massive objects, reveals dark matter's distribution even when no visible matter is present. The formation of cosmic structure itself requires dark matter. Simulations that include only ordinary matter produce a universe that looks nothing like what we observe. Only when dark matter is included, the simulations produce the cosmic web structure we see. In the context of voids, dark matter plays a critical role. While voids are underdense in galaxies, they're also underdense in dark matter, though the underdensity profiles may differ slightly. Dark matter began clustering earlier than ordinary matter, so it formed the gravitational potential wells into which galaxies later fell. In regions that became voids, dark matter was initially less dense than average, and over time, this dark matter was gravitationally pulled toward the denser regions, forming the cosmic web's filaments and clusters. Computer simulations of cosmic structure formation track the evolution of both dark matter and ordinary matter from the early universe to the present. These simulations begin with the tiny density fluctuations imprinted during the inflationary epoch and evolve them forward in time using the laws of gravity and fluid dynamics. The dark matter component is treated as a collisionless fluid, particles that interact only through gravity. The ordinary matter component, or baryonic matter, is more complex, including effects like gas pressure, cooling, heating, and star formation. When these simulations are run with cosmological parameters matching our observations of the universe, they naturally produce a cosmic web structure remarkably similar to what we observe. Voids form spontaneously as dark matter evacuates underdense regions. The largest voids in simulations match the sizes of the largest observed voids, and their density profiles, the way density changes from the void centre to its edge, also match observations. This agreement between simulation and observation strongly supports our understanding of how cosmic structure forms and evolves. For the KBC void specifically, the presence of dark matter means the void is not completely empty, even where galaxies are absent. Dark matter particles still drift through the void's interior, though in reduced numbers compared to average regions. The void's gravitational potential is shallower than surrounding regions, which affects how light travels through it, and how peculiar velocities, the motions of galaxies relative to the smooth expansion of space, develop within it. These effects are subtle but measurable, and provide additional ways to study the void's properties. There's also the intriguing question of how dark energy, the mysterious force driving the universe's accelerating expansion, interacts with voids. Dark energy appears to be a property of space itself, a constant energy density that doesn't dilute as the universe expands. In voids, where matter density is low, dark energy's influence is relatively stronger compared to gravitational attraction. This may cause voids to expand faster than denser regions, contributing to the effect we discussed earlier, where expansion rates can vary locally depending on matter density. Some researchers have proposed that studying voids might help us understand dark energy better, because voids are dominated by dark energy's influence more than denser regions are. They could serve as laboratories for probing dark energy's properties. If dark energy behaves differently than the simplest models predict, voids might be where we first detect the discrepancy. The KBC Void, if it's as large and underdense as suggested, could be particularly valuable for such studies. The interplay between dark matter, ordinary matter, and dark energy in shaping voids and the cosmic web represents one of the most profound puzzles in cosmology. We observe the effects clearly, we can model them mathematically, and we can simulate them computationally. But we still don't know what dark matter is made of, and we don't understand what dark energy fundamentally is. These unknowns remind us that despite our sophisticated understanding of cosmic structure, we're still missing crucial pieces of the universe's story. And as we contemplate the dark matter scaffolding that shapes our cosmic neighbourhood, we can appreciate that what we see with telescopes, the galaxies and stars and nebulae, represents only a small fraction of what actually exists. We're living in a universe dominated by invisible components, and our home, the KBC Void, is shaped as much by what we can't see as by what we can. Living in a cosmic void doesn't mean we're completely alone. Voids aren't perfectly empty, and the KBC Void, like all voids, contains some galaxies. These void galaxies are fascinating objects, often quite different from their counterparts in denser environments. Studying them helps us understand how galaxy formation and evolution depend on environment, and it provides clues about the nature of the void itself. Void galaxies tend to be smaller and less massive than typical galaxies found in the cosmic web's filaments or clusters. This makes sense given that voids contain less matter overall. With less raw material available, galaxies that form within voids have less mass to work with. Many void galaxies are dwarf galaxies, small systems containing millions or billions of stars rather than the hundreds of billions found in large galaxies like the Milky Way. These dwarf galaxies often have irregular shapes, rather than the grand spiral or elliptical structures characteristic of more massive galaxies. The isolation of void galaxies affects their evolution. In denser environments, galaxies frequently interact with each other. They pass close enough that their mutual gravity disrupts their structures, triggering bursts of star formation or merging entirely to form larger galaxies. These interactions are a key driver of galaxy evolution in the cosmic web's denser regions. But in voids, galaxies are so spread out that interactions are rare. A void galaxy might go billions of years without encountering another galaxy, evolving in relative solitude. This isolation has several consequences. Void galaxies tend to have more gas available for star formation, because they haven't had their gas stripped away by interactions, or by the hot gas found in galaxy clusters. As a result, many void galaxies are actively forming stars, their gas slowly condensing into new stellar generations. These galaxies can appear quite blue in colour photographs, because massive young stars shine with blue light. In contrast, galaxies and clusters often appear red because their star formation has been quenched, shut down by environmental effects, leaving only older, redder stars. The Milky Way and its neighbour Andromeda are not typical void galaxies. They're both large spiral galaxies, more massive than most void galaxies. However, the local group, the small cluster of galaxies containing the Milky Way, Andromeda, and several dozen smaller galaxies, may itself reside within the KBC Void. If so, it would be one of the more massive structures within the void, but still relatively isolated compared to galaxy groups in denser cosmic environments. The nearest large concentration of galaxies beyond the local group is the Virgo cluster, located about 50 to 60 million light-years away. This distance is significant, large enough to suggest we're in a moderately underdense region, even without invoking a large-scale void. Astronomers have catalogued void galaxies through surveys designed to identify galaxies in underdense regions. These surveys reveal that voids aren't completely devoid of galaxies, but contain perhaps 10 to 20% as many galaxies per unit volume as average regions. The exact fraction depends on the void's depth, and the type of galaxies being counted. Some voids contain relatively more small galaxies than large ones, suggesting that galaxy mass influences where galaxies can form or survive. There's also the question of how galaxies came to be in voids in the first place. Most formed there naturally from gas that happened to be in the underdense region when star formation began. But some void galaxies may have been ejected from denser regions through gravitational interactions. When two galaxies pass close to each other in a cluster or group, one might be flung outward at high velocity, escaping into the surrounding void. Such galaxies would carry the characteristics of their original environment, possibly appearing different from native void galaxies. Studying void galaxies helps test our theories of galaxy formation. If our models predict what kinds of galaxies should exist in voids, and how many there should be, we can compare these predictions to observations. Discrepancies would suggest our understanding of galaxy formation is incomplete. So far, observations of void galaxies generally agree with predictions, supporting the idea that galaxy formation is well understood across different environments, not just in the dense regions where most galaxies reside. For observers within the KBC Void, the existence of these other galaxies is reassuring. We're not in perfect isolation. If we could travel at the speed of light, we'd reach the nearest major galaxy, Andromeda, in about 2.5 million years. The Virgo cluster would take about 60 million years to reach. These are vast distances, unimaginable for human travel, but on cosmic scales they're our neighbourhood. We can see thousands of galaxies with large telescopes, study their properties, and understand our place among them. There's something poetic about the distribution of galaxies within a void. They're like islands in an ocean, scattered points of light and matter in a vast expanse of near emptiness. Each one is a system potentially containing billions of stars, perhaps countless planets, maybe even other civilizations wondering about their place in the cosmos. And all of them share this particular cosmic neighbourhood, this underdense region we call the KBC Void. As we think about these galaxies, we're reminded that despite living in a void, we're still connected to the broader universe. The light from those distant galaxies reaches us, carrying information about their stars and histories. We can study them, learn from them, and recognise that we're part of a larger community of galaxies, even if that community is more thinly spread than in other parts of the universe. And this connection extends beyond our void neighbours to the larger cosmic web and the entire observable universe, a connection we'll explore as we continue our journey through the implications of our cosmic address. At some distance from the Milky Way, perhaps 600 to 800 million light-years away, the KBC Void's underdensity begins to fade. Galaxy counts start rising back toward the cosmic average. We approach the void's edge, the boundary between our unusually empty neighbourhood and the more typical cosmic web beyond. Crossing this boundary, even conceptually, helps us understand what makes our region unusual and what lies in the universe's more densely populated regions. The void's edge isn't a sharp boundary like the surface of a planet. Instead, it's a gradual transition zone where the galaxy density increases steadily over a span of perhaps 1 or 200 million light-years. At the very edge, we'd find ourselves in a region of approximately average density, neither particularly empty nor particularly full. Continue farther, and we'd enter the walls and filaments of the cosmic web proper, regions where galaxy density is significantly above average. Some of the nearest major structures beyond the KBC Void's presumed edge include the Shapley supercluster, an enormous concentration of galaxies located roughly 650 million light-years from Earth. The Shapley supercluster is one of the largest structures in the nearby universe, containing tens of thousands of galaxies arranged in clusters and groups. Its total mass is perhaps 10,000 times that of the Milky Way, and its gravitational pull influences galaxy motions over hundreds of millions of light-years. In another direction, we find the Sloan Great Wall, a vast filament of galaxies discovered in the Sloan Digital Sky Survey. This structure stretches over 1 billion light-years in length, though it's much thinner in the other dimensions, forming a sheet or wall of galaxies. The Sloan Great Wall represents the typical cosmic web structure at its most dramatic, a dense concentration of matter tracing out the large-scale structure of the universe. These structures provide a contrast to our void. While we see perhaps 30 to 40% fewer galaxies than average in our local region, these overdense structures contain 2 or 3 times as many galaxies as average, packed into filaments and clusters. The environment there is profoundly different. Galaxies interact frequently, merging and triggering bursts of star formation. Hot gas fills the space between galaxies, particularly in massive clusters. The night sky, if viewed from a planet in such a region, would be remarkably different, crowded with bright galaxies visible to the naked eye rather than the relative emptiness we see from Earth. Mapping the transition from void to wall helps confirm the void's existence and measure its size. If we were in an average region falsely appearing under dense due to observational errors, we wouldn't see a clear transition to higher density at a consistent distance in multiple directions. But surveys suggest we do see such transitions, with galaxy density rising as we move outward from our position. This pattern is consistent with being near the centre of a large void, with well-defined edges. The existence of structures like the Shapley supercluster and Sloan Great Wall beyond our void also helps explain large-scale flows of galaxies. Galaxies don't simply move with the expansion of space. They also have peculiar velocities, motions relative to the expansion caused by gravitational attraction to massive nearby structures. The Milky Way, for instance, is being pulled toward the Shapley supercluster, creating a component of our motion through space that's independent of cosmic expansion. These large-scale flows were puzzling when first discovered because they suggested massive structures beyond what was then known. Now, with better maps of the cosmic web, we can account for these flows by identifying the massive structures responsible. If we live in a void, the pattern of peculiar velocities around us should show galaxies near the void's edge being pulled outward toward the denser walls, while those deep inside the void might drift slowly toward the nearest concentrations of matter. This creates a pattern of outflow from the void's interior. Observations of peculiar velocities are challenging because they require very precise distance measurements, but improving data is beginning to test these predictions. There's also the question of what happens at the boundary between voids and filaments in terms of dark energy and cosmic expansion. Some theoretical models suggest that the transition zone might have interesting properties, perhaps influencing how expansion proceeds or how light travelling through the region is affected. These effects would be subtle, but they could potentially be detected through careful observations of distant supernova or the cosmic microwave background as seen through different lines of sight. Looking beyond our void reminds us that the KBC Void, as large and unusual as it may be, is just one feature in a universe filled with structure at all scales. The cosmic web extends throughout the observable universe, a vast tapestry of voids, filaments, walls, and clusters shaped by billions of years of gravitational evolution. Our void is part of this tapestry, a particularly sparse region within a larger pattern that encompasses everything we can see. And recognizing this larger context helps us appreciate both our uniqueness and our connection to the whole. We may live in an unusually empty region, but that region formed through the same physical processes that created every other feature in the cosmos. We're special in our circumstances, but not in the laws that govern us. And as we move from mapping the void to understanding what it means for cosmology, we carry this sense of connection with us. The possibility that living in the KBC Void could resolve the Hubble tension is tantalizing, but it raises an important question. Could it solve the tension completely, or is it only part of the answer? To explore this, we need to look carefully at the numbers and at what the void hypothesis actually predicts about local and global expansion rates. Recall that the local measurements of the Hubble constant, primarily using the cosmic distance ladder method, give values around 73 kilometers per second per megaparsec. The cosmic microwave background measurements give about 67. The difference is roughly 9%, and both measurements have uncertainties of only a few percent. This means the discrepancy is statistically significant, larger than the measurement errors, and has persisted even as the measurements have improved. If we attribute this discrepancy entirely to living in a void, we need the void to create a local expansion rate about 9% higher than the global average. Theoretical calculations show that a void can indeed create such an effect, but it requires the void to be quite large and quite underdense. A void roughly 1 billion light-years across with a density about 30 to 40% below average could potentially create the needed difference. This is encouragingly close to the properties estimated for the KBC Void based on Galaxy surveys. However, the exact numbers depend on details that are still uncertain. Where precisely do we sit within the void? If we're exactly at the centre, the effect would be maximised. If we're offset toward one edge, the effect would be reduced. What is the void's exact density profile? A void that's very underdense at the centre but returns quickly to average density at the edge would create a different effect than one with a more gradual profile. And how do we account for the presence of structures like the local group and the Virgo cluster within or near the void? These local concentrations of matter complicate the simple picture of a uniform underdensity. Some theoretical studies suggest the void could account for the entire Hubble tension. These studies model the void's gravitational effects on light propagation and on the expansion rate within the void, finding that the combination of effects can plausibly explain the full discrepancy. Other studies are more conservative, suggesting the void could explain perhaps half of the tension. Reducing the discrepancy from 9% to 4 or 5%, this would still leave a residual tension requiring either additional explanations or a revision of one of the measurement methods. There's also the question of whether other cosmological observations are consistent with the void hypothesis. For instance, measurements of baryon acoustic oscillations, a feature imprinted in the distribution of galaxies by sound waves in the early universe, provide another way to measure cosmic expansion. These measurements give values intermediate between the local and global measurements, which is interesting. If we live in a void, we might expect our baryon acoustic oscillation measurements to reflect a local expansion rate somewhere between the void interior and the cosmic average, which is roughly what's observed. Another piece of evidence comes from studies of Type 1 supernovae at various distances. If the void hypothesis is correct, supernovae at different distances should show systematic variations in their apparent brightness related to the void's density profile. Supernovae within the void should appear slightly dimmer than expected based on their redshift because light travels through an underdense region. Supernovae beyond the void's edge should appear brighter. Some studies claim to detect these patterns, while others find the data too noisy to confirm the effect definitively. The possibility that the void might solve the Hubble tension entirely is appealing, because it doesn't require new physics. We don't need to modify general relativity, postulate new particles, or revise our understanding of dark energy. We simply need to acknowledge that our local environment is unusual, and our local measurements reflect local conditions. This is a conservative explanation in the best sense, invoking known physics applied to an unusual but not impossible situation. However, the conservative nature of the explanation doesn't make it automatically correct. Science requires that we test predictions rigorously and remain open to alternative explanations. Some researchers argue that systematic errors in the distance ladder method, particularly in the calibration of Cepheid variable stars, could account for part or all of the Hubble tension without requiring a void. Others propose modifications to dark energy, or the introduction of new physics in the early universe. Each possibility has its proponents and must be evaluated on its evidence. What's needed is a decisive test, an observation that could clearly distinguish between the void hypothesis and alternatives. One such test involves measuring the Hubble constant, using methods that don't rely on the cosmic distance ladder and that sample different regions of space. For example, gravitational wave observations from merging neutron stars can provide independent distance measurements when combined with observations of the electromagnetic counterparts. If these measurements, which sample our local cosmic volume, give values consistent with the local distance ladder measurements, that would support the idea that our local region genuinely has a higher expansion rate. Another approach involves mapping the void's extent more precisely. If the void's size and depth can be confirmed through multiple independent galaxy surveys, and if theoretical models using those confirmed parameters can quantitatively reproduce the observed Hubble tension, that would strengthen the case significantly. Conversely, if better surveys show the void is smaller or less underdense than initially thought, the hypothesis would be weakened. The question of whether the void solves everything remains open, a topic of active research and debate. What's clear is that the void offers a plausible, testable explanation that fits within our current understanding of cosmology. Whether it's the complete answer, part of the answer, or ultimately not the answer will be determined by ongoing observations and careful analysis. And as we ponder this possibility, we can appreciate the scientific process at work, the way evidence accumulates, hypotheses are tested, and our understanding gradually converges on truth, even when that truth reveals that we live in an unusual corner of the cosmos. While the KBC Void hypothesis offers an intriguing potential solution to the Hubble tension, it's important to consider other explanations that have been proposed. The tension might arise from systematic errors in measurements, from new physics we haven't yet discovered, or from a combination of factors. Examining these alternatives helps us appreciate the complexity of the problem and the care required to solve it. On the other side of the tension, some researchers have questioned whether the cosmic microwave background measurements are being interpreted correctly. The standard model of cosmology used to derive the Hubble constant from the CMB assumes certain properties of dark matter, dark energy, and the universe's curvature. If any of these assumptions are wrong, the derived Hubble constant would be wrong too. For instance, if dark energy behaved differently in the early universe than it does today, the CMB predictions would change. This possibility, sometimes called early dark energy, has been explored theoretically, with mixed results. Another alternative involves modifications to general relativity itself. Einstein's theory of gravity has been tested extensively and has passed every test with remarkable precision. But perhaps, on the largest cosmic scales, or in the presence of dark energy, gravity behaves slightly differently than general relativity predicts. Modified gravity theories have been proposed to explain cosmic acceleration without invoking dark energy, and some of these theories might also affect how we interpret cosmological measurements. However, most modified gravity theories face challenges in explaining other observations, and there's no consensus on which, if any, might be correct. There's also the possibility of new physics in the neutrino sector. Neutrinos are nearly massless particles produced in vast numbers in the early universe. Their properties affect the cosmic microwave background and the growth of cosmic structure. If neutrinos have unexpected properties, such as additional interactions beyond those in the standard model of particle physics, this could alter the predictions derived from the CMB. Some researchers have explored models with extra neutrino species or with neutrinos that interact through new forces, finding that such models can sometimes help alleviate the Hubble tension. Each of these alternative explanations has been investigated thoroughly. Some can partially reduce the tension, bringing the two measurements closer together. But none has emerged as a clear, comprehensive solution that explains the full discrepancy while remaining consistent with all other cosmological observations. This is why the void hypothesis is compelling. It offers a relatively simple explanation that doesn't require new physics or questioning our fundamental theories, just an acknowledgement that our local environment is unusual. However, it's possible that the true explanation involves a combination of factors. Perhaps we do live in a void that contributes a few percent to the tension, and there's also a small systematic error in the distance measurements that contributes another few percent. Or perhaps the void effect is real but smaller than needed, and there's also subtle new physics that makes up the difference. Science often finds that reality is more complex than any single simple explanation suggests. What's crucial is that we continue testing all possibilities rigorously. We need better distance measurements using independent methods. We need more detailed maps of our local cosmic structure. We need more precise measurements of the cosmic microwave background and of large-scale structure. And we need theoretical work exploring how different physical scenarios would manifest in observations. Only through this comprehensive approach can we hope to resolve the tension definitively. The fact that the Hubble tension exists at all is remarkable. It suggests we're on the verge of discovering something important about the universe, whether that's the realization that we live in an unusual place, the discovery of new physics, or the identification of subtle measurement challenges. Any of these outcomes would advance our understanding significantly, and as we contemplate these possibilities, we can appreciate the beauty of cosmology as a science. We're trying to understand the universe as a whole using observations from a single vantage point, applying physical laws derived from experiments on Earth to processes occurring across billions of light years. That we can do this at all is remarkable. That we can identify tensions and inconsistencies suggests our methods are robust enough to detect genuine problems. And that we have multiple promising avenues for resolving those tensions gives hope that we'll eventually arrive at a complete and consistent understanding. If we accept, at least provisionally, that we live inside the KBC Void, what does this mean for us practically? How does it affect our observations of the universe, our understanding of our cosmic neighbourhood, and our search for answers to fundamental questions? The implications extend beyond the Hubble tension to several areas of astronomy and cosmology. First, living in a void affects how we observe distant structures in the universe. Light from distant galaxies travels through the void to reach us, and the void's underdensity affects that light's journey. Gravitational lensing, the bending of light by mass, is weaker in underdense regions than in denser ones. This means that light from very distant objects such as quasars or early galaxies might be slightly less distorted when it passes through our void compared to what it would experience in an average region. The effect is subtle, but it's measurable in principle, and it could influence how we interpret observations of distant cosmic phenomena. There's also the question of what future observations might reveal. If the void hypothesis is correct, then as observational techniques improve and surveys extend farther, we should see the void's edge more clearly, confirming its extent and depth. We might also discover other voids of comparable size in the distant universe, demonstrating that such structures, while rare, are not unique. Alternatively, improved data might show that the underdensity is less significant than currently estimated, or that it doesn't extend as far, which would weaken the void hypothesis and require alternative explanations for the Hubble tension. The implications for cosmology are profound. If local measurements genuinely reflect local conditions rather than universal averages, it changes how we interpret data. It means that not every cosmological measurement samples the same cosmic properties. Some measurements tell us about our local environment, while others tell us about the universe as a whole. Distinguishing between these becomes crucial for deriving accurate cosmological parameters. Moreover, recognizing that we might live in an unusual location encourages humility and caution in cosmology. We must always ask whether our observations are representative of the universe at large, or whether they're biased by our particular cosmic address. This is a healthy form of skepticism, one that drives us to test our assumptions and to seek observations from as wide a variety of cosmic environments as possible. In practical terms, living in a void doesn't change our daily experience or our local observations of stars and planets. The Milky Way remains unchanged, the laws of physics are the same, and the universe's beauty and mystery persist undiminished. What changes is our understanding of our place in the larger cosmic structure, our awareness that the region of space we call home is somewhat less crowded than average. a vast chamber in the cosmic web's intricate architecture. And there's something quietly beautiful about this realization. We're not in the densest, most active regions of the universe where galaxies collide frequently and stars form in great bursts. We're in a quieter neighbourhood, a place where space is given room to breathe, where galaxies are scattered like distant islands rather than crowded cities. It's a place where we can observe the universe with less local interference, where our view outward is less obstructed by nearby structures. In this sense, our void might offer certain advantages for cosmic observation, even as it presents challenges for understanding our local expansion rate. Science advances through testing hypotheses, through designing observations and experiments that could distinguish between competing explanations. The KBC Void hypothesis makes specific predictions that can be tested, and numerous research programs are underway or plan to do exactly that. Understanding these tests helps us appreciate how scientific certainty is built gradually through the accumulation of evidence. Another test involves measuring the Hubble constant using independent methods that sample different regions of space. Gravitational waves from merging black holes and neutron stars can provide distance measurements when combined with electromagnetic observations of the merger. These events can be seen at various distances, both within and potentially beyond the void. If the void hypothesis is correct, gravitational wave standard sirens within the void should give Hubble constant measurements consistent with the local distance ladder measurements, while those beyond the void should give values closer to the CMB prediction. Observing this pattern would strongly support the void hypothesis. Observations of the integrated Sachs-Wolf effect offer another avenue. The CMB temperature should show subtle correlations with the positions of large voids, appearing slightly warmer in those directions. Improved CMB data from experiments like the Simons Observatory and future space missions will measure these correlations more precisely. A clear detection of the ISW signal from the KBC Void would provide independent confirmation of its existence and depth. Measurements of baryon acoustic oscillations at different distances provide yet another test. BAO measurements within the void should reflect the local density and expansion rate, while those at the void's edge or beyond should reflect the transition to average conditions. By carefully analysing how BAO signals vary with distance and direction, cosmologists can map the void structure and test whether it has the properties needed to explain the Hubble tension. There's also the possibility of using supernovae to probe the void's density profile. Type 1. A supernova at various distances can serve as probes of both distance and cosmic expansion. If the void creates the predicted effects on light propagation and expansion rates, supernovae within the void should show systematic deviations from expectations compared to a homogeneous universe. Specifically, the relationship between supernova brightness and redshift should show small but detectable differences depending on whether the supernova is within the void, at its edge, or beyond it. Ongoing supernova surveys are collecting the data needed for such tests. Theoretical work is equally important. Cosmologists are running increasingly sophisticated simulations of cosmic structure formation, asking whether voids as large as the KBC Void can form naturally in a universe with our observed properties. These simulations start from the initial conditions set by the cosmic microwave background and evolve the distribution of matter forward to the present day. By analysing the voids that form in these simulations, researchers can determine whether KBC-like voids are rare but plausible, or so improbable that their existence would challenge our cosmological model. Some simulations suggest that voids of the required size and depth are uncommon, but not impossibly so. They occur in perhaps a few % of simulated universes, consistent with the idea that we might live in one simply by chance. Other simulations, particularly those using slightly different cosmological parameters, find such voids to be extremely rare, raising questions about whether the void hypothesis is statistically viable. Reconciling these different simulation results and comparing them carefully to observations is an ongoing challenge, There's also the question of consistency with other cosmological observations. The void hypothesis must not only explain the Hubble tension, but also remain consistent with measurements of cosmic age, the density of matter and dark energy, the growth rate of cosmic structure, and numerous other well-established results. Any explanation for the tension that solves one problem while creating others would not be acceptable. The void hypothesis generally passes these consistency tests, but careful checks are essential. And as we await these results, we can appreciate the journey itself, the process of scientific discovery unfolding in real time, the way each new observation adds a piece to the puzzle, bringing us closer to a complete and accurate picture of the cosmos. As we reach the midpoint of our journey through the KBC Void, it's worth pausing to contemplate what it means to live in such a place from a more reflective, almost meditative perspective. Beyond the scientific implications, beyond the measurements and tensions and theoretical models, there's something profound about the simple fact of inhabiting a quieter, less crowded region of the universe. Imagine, if you will, the universe as a vast city. The cosmic web's filaments and clusters are the busy downtown areas, places crowded with galaxies where interactions are frequent and the pace of evolution is rapid. Stars form in great bursts, galaxies collide and merge, supernovae explode with regularity. These are dynamic, energetic environments, full of activity and change. They're fascinating to study. And they contain most of the universe's visible matter and energy. Now imagine the voids as the suburbs and countryside surrounding these urban centres. The pace is slower here. Galaxies are scattered widely, evolving more independently, less influenced by their neighbours. Star formation continues, but at a more measured pace. There is space to breathe, distance between structures, a sense of openness and quiet. This is where we live, in one of these quieter neighbourhoods, not in the bustling centre but in the spacious periphery. There's no judgment implied in this comparison. Living in a void isn't better or worse than living in a dense cluster, just different. Each environment has its own character, its own advantages and challenges. In dense environments, the frequency of galaxy interactions drives rapid evolution and creates spectacular phenomena. In voids, the isolation allows for more gradual, undisturbed development. Both are natural outcomes of cosmic structure formation, different expressions of the same fundamental physics. For us as observers, living in a void means we have a relatively clear view outward. We're not surrounded by nearby bright galaxies that might overwhelm our instruments or obstruct our view of more distant objects. When we look deep into space with our most powerful telescopes, we're seeing across the void and beyond it, observing the universe's dense regions from a distance. This separation provides perspective, allows us to study cosmic structure from outside the most crowded areas. It also means our night sky is relatively dark and quiet. The Milky Way dominates our view. A river of stars arcing across the sky, but beyond our galaxy, the nearest bright spiral is Andromeda, 2.5 million light-years away. A resident of a galaxy in a massive cluster might see dozens of bright galaxies scattered across their sky, fellow cluster members close enough to appear as distinct fuzzy patches. Our sky is comparatively empty, which has allowed humans to develop a certain perspective on the cosmos. To recognise our galaxy's isolation and to contemplate the vast distances between stellar systems. This cosmic address might have influenced how we developed our understanding of the universe. If we lived in a dense cluster surrounded by nearby galaxies, we might have recognised the universe's scale earlier in our scientific history. The abundance of nearby galaxies would have been obvious even with modest telescopes. Instead, we spent centuries thinking the Milky Way might be the entire universe, only realising in the 20th century that the spiral nebulae were external galaxies. Our isolation made this discovery harder, but it also made it more profound when it finally came. There's also a sense in which living in a void connects us to the concept of cosmic loneliness. We're in a region where matter is sparse, where the distance between galaxies is greater than average. In the far future, as the universe continues expanding and dark energy drives cosmic acceleration, the voids will grow larger and emptier. Galaxies in voids will become increasingly isolated as expansion carries their neighbours beyond the cosmic horizon, the distance beyond which light can never reach us. Living in a void now means we're already in an environment that prefigures this future cosmic isolation. But loneliness is perhaps the wrong word. Isolation can also mean independence, the freedom to develop without constant interference. For our galaxy and our solar system, being in a relatively empty region has meant fewer close encounters with other galaxies, fewer disruptions, perhaps a more stable environment for the long, slow process of stellar and planetary evolution. It's possible that complex life requires such stability, that crowded cosmic neighbourhoods are too chaotic for life to develop and persist over billions of years. This touches on questions about the distribution of life in the universe. If habitable environments are more common in quieter cosmic neighbourhoods, then voids might actually be favoured locations for life despite their lower galaxy density. Fewer galaxies but more stable environments could 90 minutes. You've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. Fewer galaxies but more stable environments could balance out, making life's abundance similar in voids and denser regions. Or perhaps life is rare everywhere, and the environment matters less than we imagine. These questions remain open, fascinating topics for future exploration. What's certain is that our location in a void is part of our cosmic story, part of what makes our perspective on the universe unique. Every observer in the cosmos has a unique vantage point, shaped by their position in space and time. Ours happens to be in a large underdense region. And that fact colours our observations and influences the questions we ask. Understanding this helps us interpret our data more accurately, and reminds us that what we see from here might not represent the universe's average conditions. There's beauty in this realisation. We're not just passive observers of an objective, uniform cosmos. We're participants in a universe of incredible diversity, where structure exists at all scales, and where every location offers a slightly different window on the whole. Our void is our window, our particular view, and through it, we're learning about the universe's grand architecture and our modest place within it. As we rest here at the centre of our journey, let that thought settle. We live in a void, a vast underdense bubble in the cosmic web, one of the largest structures of its kind in the observable universe. And from this quiet corner, we've reached out to understand the cosmos entire, mapping distant galaxies, measuring the universe's expansion, probing the nature of dark matter and dark energy. Our location hasn't limited us. If anything, it's given us a unique perspective, a viewpoint from which we can appreciate the universe's structure more clearly, because we're not lost in the densest parts, but observing from the spacious margins. To fully appreciate the KBC Void, we need to step back and consider the universe's structure at the very largest scales. When we map the distribution of galaxies across billions of light years, a remarkable pattern emerges. The universe resembles a foam or sponge, with matter concentrated in thin sheets and filaments surrounding vast empty bubbles. This foam-like structure is one of the most fundamental features of the cosmos, and understanding it helps us place our void in its proper context. The foam structure wasn't predicted before it was observed. Early cosmologists working in the mid-20th century generally assumed the universe would be relatively smooth and uniform on large scales. They knew galaxies clumped together in groups and clusters, but they expected these clumps to be scattered more or less randomly through space, like raisins in bread dough. The discovery of the cosmic web structure, with its filaments and voids, came as a surprise. This structure emerged from careful mapping of galaxy positions beginning in the 1970s. As redshift surveys measured the three-dimensional positions of more and more galaxies, patterns became evident. Galaxies lined up in sheets and filaments, creating walls that enclosed large empty regions. The Coma Wall, a vast sheet of galaxies extending across hundreds of millions of light-years, was one of the first such structures recognized. The discovery of the Botas Void in 1981 confirmed that the empty regions were real features, not observational artifacts. Theoretical work soon explained why this structure forms. The tiny density fluctuations in the early universe, seeded during cosmic inflation, evolved under gravity's influence. Dense regions collapsed while underdense regions expanded, creating a network of overdense and underdense regions. The mathematics of this process naturally produces a foam-like structure. In 3 dimensions, gravitational collapse along multiple axes creates sheets and filaments where matter concentrates, while expansion of underdense regions creates the voids. Computer simulations of cosmic structure formation beautifully reproduce this foam structure. Starting from the initial conditions measured in the cosmic microwave background, simulations evolve billions of dark matter particles forward in time using only gravity. The particles clump along filaments and at nodes, creating a cosmic web remarkably similar to what we observe in galaxy surveys. The largest simulations today evolve trillions of particles in volumes comparable to the observable universe, and they show that the foam structure is a universal feature, present at all cosmic epochs, from the early universe to today. The scale of this structure is extraordinary. Individual filaments can stretch for hundreds of millions of light years, connecting galaxy clusters like bridges spanning cosmic gulfs. The sheets or walls can be even larger, extending over 1 billion light-years in length and width, but only a few tens of millions of light-years thick. And the voids, the empty chambers in the foam, range from about 50 million light-years for the smallest to nearly 1 billion light-years for the largest, like the KBC Void. This structure is hierarchical, meaning it exists at multiple scales simultaneously. Small voids sit within larger voids. Small filaments branch off from larger ones. The cosmic web has structure on scales from a few million light-years, where individual galaxy groups reside, up to several hundred million light-years, the scale of the largest supervoids and superclusters. Beyond about 1 billion light-years, the universe begins to look more uniform, the foam averaging out to a relatively smooth distribution when viewed at the very largest scales. This perspective, this recognition that our environment is one instance of a type that occurs throughout the cosmos, brings a kind of humility and connection. We're unusual but not unique, special in detail but not in kind. And that's precisely the kind of understanding the Copernican principle encourages. Recognizing our place without claiming cosmic privilege, understanding our uniqueness without losing sight of our connection to the universal whole. Voids serve as more than just structural features in the cosmic web. They're also laboratories for studying dark energy, the mysterious component that makes up about 70% of the universe's energy density and drives cosmic expansion to accelerate. Because voids are dominated by dark energy more than denser regions are, studying void properties can help us understand dark energy's nature and behaviour. Dark energy was discovered through observations of distant Type 1, a supernova in the late 1990s. Astronomers expected the universe's expansion to be slowing down over time due to the gravitational attraction of matter, pulling everything back together. Instead, they found that the expansion is accelerating, speeding up as time passes. This acceleration requires a repulsive force, something pushing space apart rather than pulling it together. Dark energy is the name given to whatever causes this acceleration. The simplest explanation for dark energy is that it's a cosmological constant, a property of space itself with constant energy density everywhere and at all times. Albert Einstein originally introduced the cosmological constant into general relativity to allow for a static universe, then abandoned it when the universe's expansion was discovered. The irony is that the cosmological constant turns out to be real, just with a very small value that causes acceleration rather than keeping the universe static. If dark energy is truly a cosmological constant, then its effects should be identical everywhere, in voids and clusters alike. But dark energy might not be so simple. It could be a dynamical field, something that changes over time or varies from place to place. Such fields, generically called quintessence, could have energy densities that evolve as the universe ages, or that respond to the local environment. If dark energy is quintessence, its effects might differ between voids and denser regions, creating observable signatures that could help distinguish it from a pure cosmological constant. Voids are ideal places to search for such signatures because dark energy dominates there more completely than elsewhere. In a galaxy cluster, the gravitational pull of the cluster's enormous mass is the dominant force, and dark energy's effect is relatively weak. But in a void, where mass density is low, dark energy's repulsive effect is proportionally stronger. The balance between gravity and dark energy tips decisively toward dark energy in voids, making them sensitive probes of dark energy's properties. One way to study dark energy in voids involves measuring void shapes and how they evolve over time. If dark energy is a cosmological constant, voids should expand at a predictable rate, growing larger and emptier as the universe ages. If dark energy is something more complex, voids might expand differently, either faster or slower depending on dark energy's specific properties. By measuring void sizes at different cosmic epochs, using galaxies at different distances, astronomers can test whether void evolution matches the predictions of a cosmological constant. Another approach looks at how voids affect the growth of cosmic structure. Dark energy slows structure growth by accelerating expansion, which pulls matter apart faster than gravity can pull it together. This effect is most pronounced in underdense regions like voids. By measuring how quickly galaxies and dark matter clump together in voids compared to denser regions, cosmologists can test whether dark energy behaves as expected. Deviations from predictions might indicate that dark energy is more complex than a cosmological constant. As telescopes and surveys improve, our ability to use voids as dark energy probes will increase. The Vera Rubin Observatory will map millions of galaxies in voids, measuring their positions and properties with unprecedented precision. The Euclid Space Telescope will study void shapes and evolution across cosmic time. These observations will constrain dark energy's properties far better than current data allows, potentially revealing whether it truly is a cosmological constant or something more intriguing. The connection between voids and dark energy reminds us that cosmology's great mysteries are interconnected. The Hubble tension, the nature of dark energy, the properties of dark matter, and the large-scale structure of the universe all relate to each other. Understanding voids helps us understand dark energy, which helps us understand cosmic expansion, which helps us resolve tensions in our measurements. Each piece of the puzzle informs the others, and progress in one area often leads to insights in another, and as we contemplate dark energy's role in shaping our void, we can appreciate how much remains unknown about the universe, despite our sophisticated understanding. We can map cosmic structure across billions of light years. We can detect tiny temperature fluctuations in the cosmic microwave background. We can measure distances to galaxies with remarkable precision. Yet we still don't know what makes up most of the universe's energy density, or why it causes space to accelerate outward. These mysteries keep cosmology vibrant and exciting, full of discoveries yet to be made. The KBC Void we observe today is not static. It has evolved over billions of years, growing larger and emptier as the universe has expanded and aged. Understanding this evolution connects our void to cosmic history, showing how it emerged from the early universe's near uniformity and how it will continue changing in the future. In the beginning, moments after the Big Bang, the universe was remarkably smooth. Density variations were tiny, only about 1 part in 100,000. These small fluctuations imprinted during cosmic inflation were the seeds from which all structure grew. In the regions that would become the KBC Void, the density was slightly lower than average, just a fraction of a percent less than the cosmic mean. This tiny difference was enough. As the universe expanded and cooled, gravity began amplifying these small fluctuations. Denser regions attracted matter from their surroundings, growing denser still. Underdense regions lost matter to the denser areas, becoming more underdense. This process was slow at first, for the first few 100 million years after the Big Bang. Radiation pressure in the hot, dense universe resisted gravitational collapse, keeping matter relatively smooth. Only after the universe cooled sufficiently for matter to dominate over radiation could significant structure begin forming. By the time the universe was about 1 billion years old, the first galaxies had formed, clustering along the emerging filaments of the cosmic web. The regions that would become voids were already recognizable as underdense areas, though they still contained more matter than they do today. Over the next several billion years, these underdense regions continued to lose matter to the surrounding filaments and clusters, gradually emptying out. The voids grew larger as the universe expanded, and they grew more underdense as matter continued draining toward higher density regions. The KBC Void's evolution can be traced through its current properties. Its size, roughly 1 billion light-years, tells us about the scale of the initial density fluctuation that seeded it. Its depth, the degree of underdensity, tells us how much matter has been evacuated and how long the process has had to operate. Theoretical models can work backward from the present-day void to estimate what the region looked like at earlier times, reconstructing its evolutionary history. About 7 billion years ago, when the universe was roughly half its current age, the KBC Void would have been noticeably smaller and less underdense. It might have measured only 500 or 600 million light-years across, and its density deficit might have been only 20 or 30% rather than the 40% or so observed today. Galaxies that now lie beyond the Void's edge would have been within it, and the galaxy density throughout the region would have been higher. The Void's evolution accelerated as dark energy became dominant in the universe. About 5 or 6 billion years ago, the universe's expansion began accelerating, driven by dark energy overcoming the gravitational pull of matter. This acceleration preferentially affects voids because they have less mass to resist dark energy's push. As expansion accelerated, voids expanded faster than denser regions, growing larger and more underdense at an increasing rate. The KBC Void's current size and depth reflect this accelerated evolution. Looking forward, the void will continue growing. As the universe expands further and dark energy remains dominant, the void will become even larger and emptier. In tens of billions of years, it might measure several billion light-years across, and its density could drop to a fraction of what it is now. Galaxies currently within the void will drift farther apart, and eventually they may lose sight of each other entirely as cosmic expansion carries them beyond each other's cosmic horizons. This future evolution connects to profound questions about the universe's ultimate fate. If dark energy truly is a cosmological constant, the universe will expand forever, accelerating without limit. Voids will grow indefinitely, eventually occupying nearly all the universe's volume. Galaxies within voids will become increasingly isolated, their night skies growing darker as neighbouring galaxies recede beyond observable distance. In the extreme far future, trillions of years from now, civilizations in void galaxies might observe a universe containing only their own galaxy, with no evidence of external galaxies remaining visible. This possible future highlights the importance of our current cosmic epoch. We live at a time when the universe's large-scale structure is clearly visible, when we can observe the cosmic web and measure its properties. In the distant past, when the universe was younger and smaller, the structure was less developed. In the distant future, as voids expand and galaxies recede, the structure will become increasingly difficult to observe. We're in a golden age for cosmology. A brief window in cosmic history when the universe's structure is both well developed and readily observable. The void's evolution also affects how we interpret observations. When we look at distant galaxies, we're seeing them as they were billions of years ago, when the light we observe began its journey. If those galaxies are in voids, we're seeing those voids at earlier stages of evolution, when they were smaller and less underdense. By comparing voids at different distances, and thus at different cosmic epochs, astronomers can study how voids evolve, testing whether the observations match predictions from cosmic structure formation theory. Some studies have attempted this, identifying voids in galaxy surveys at various redshifts and measuring their properties. The results generally support the idea that voids grow and become more underdense over time, consistent with predictions. However, the measurements are challenging because distant voids are harder to identify and characterize than nearby ones. Improved surveys will allow more detailed studies of void evolution across cosmic time. Understanding void evolution also helps us appreciate the dynamic nature of cosmic structure. The universe isn't a static arrangement of galaxies frozen in space. It's a constantly evolving system where structure grows, changes, and eventually, under dark energy's influence, begins to disperse. Voids are part of this evolution, regions that started slightly underdense and have been growing emptier ever since. In a sense, voids represent the universe's tendency toward entropy on the largest scales. Regions where matter is drained away and dark energy's influence approaches dominance. Our residence in such a region places us in the middle of this grand evolutionary process. The KBC Void is older than our solar system, having been growing for over 13 billion years. It will continue growing long after the sun has died and our galaxy has evolved beyond recognition. We're temporary inhabitants of a structure that exists on timescales far exceeding human or even stellar lifetimes. Witnesses to a brief moment in its long evolution. There's a kind of poetic resonance in this realization. We live in a void that's simultaneously ancient and still evolving, a structure shaped by the entire history of the universe and continuing to change as the future unfolds. Our observations of this void are snapshots of a process spanning cosmic ages, and our understanding connects the deepest past to the farthest future in a single coherent narrative. As we approach the final third of our journey, it's fitting to step back and consider our complete cosmic address, placing the KBC Void in the context of all the structures and scales that define our location in the universe, from the smallest to the largest, from our planet to the edges of the observable cosmos. Each level of structure tells part of the story of where we are. We begin with Earth, a rocky planet orbiting a middle-aged star. Earth is the third planet from the Sun, located in the habitable zone where liquid water can exist on a planet's surface. Our planet formed 4.5 billion years ago from the disk of gas and dust that surrounded the young sun, accreting slowly from countless collisions of smaller bodies. It's our home, the only place in the universe where we know life exists, a blue and green oasis in the darkness of space. The Sun is one star among hundreds of billions in the Milky Way galaxy. It resides in a relatively quiet region of the galaxy's disk, about 2/3 of the way out from the galactic centre, in a minor spiral arm called the Orion Arm, or Orion Spur. The Sun orbits the galactic centre once every 220 million years or so, carrying the solar system with it. We're not in a particularly dense or sparse region of the galaxy, just an ordinary part of the disk where star formation continues at a modest pace. The Milky Way itself is a large spiral galaxy, measuring about 100,000 light-years across and containing perhaps 200 to 400 billion stars. It's accompanied by numerous smaller satellite galaxies, dwarf galaxies that orbit the Milky Way like moons orbit a planet. The most prominent satellites are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light. These satellites are being slowly torn apart by the Milky Way's gravity, their stars and gas eventually being incorporated into our galaxy. Our galaxy belongs to the Local Group, a small cluster of galaxies spanning about 10 million light-years. The Local Group contains 3 large spirals: the Milky Way, Andromeda, and Triangulum, plus several dozen smaller galaxies. Andromeda, also called M31, is the nearest large galaxy. About 2.5 million light-years away, it's slightly larger than the Milky Way and is approaching us at about 110 kilometers per second. In about 4 billion years, Andromeda and the Milky Way will collide and merge, forming a giant elliptical galaxy that astronomers have nicknamed Milkomeda. The Local Group is part of the Laniakea supercluster, an enormous structure spanning about 500 million light-years and containing roughly 100,000 galaxies. Laniakea isn't a gravitationally bound structure like a galaxy cluster. It's a region defined by common motion, a vast flow of galaxies being pulled toward a central attractor called the Great Attractor. The Milky Way and the Local Group are on the outskirts of Laniakea, being pulled toward its centre, along with thousands of other galaxies. Our complete address, then, reads something like this: Earth, third planet from the Sun, in the Orion arm of the Milky Way galaxy, part of the Local Group, on the outskirts of the Laniakea supercluster, within the KBC Void, in the observable universe, possibly one region within an infinitely larger cosmos. Each level of this address situates us more completely, connecting our immediate surroundings to ever larger structures and scales. There's something both humbling and empowering about contemplating this address. Humbling because it reveals how small we are, how our entire planet is an insignificant speck within structures so vast they defy imagination. Empowering because it shows what we've accomplished in understanding our place. From our tiny world, using observations and reason, we've mapped the universe across billions of light-years, identified structures at scales millions of times larger than our galaxy, and determined our location within this grand cosmic architecture with remarkable precision. This knowledge connects us to the universe in profound ways. We're not separate from the cosmos, observing it from outside. We're embedded within it, part of its structure, our atoms formed in stars that lived and died long before the sun existed, our planet assembled from material created in the Big Bang and processed through generations of stellar nucleosynthesis. The void we live in shaped the environment where our galaxy formed, influencing the conditions that allowed a solar system like ours to develop, that enabled a planet like Earth to coalesce and cool, that permitted life to arise and evolve into beings capable of asking questions about their cosmic address. Understanding our address doesn't answer every question about our existence or purpose, but it provides context. It reminds us that we're products of cosmic evolution, that our presence here is connected to the largest structures and processes in the universe. The KBC Void, in this sense, isn't just a scientific curiosity or a potential solution to the Hubble tension. It's part of our story, part of what makes us who and where we are. And as we hold this complete cosmic address in our minds, we can let it settle, can appreciate the remarkable fact that we know it at all, that 13 billion years of cosmic history and human curiosity have brought us to this moment of understanding. As we enter the final arc of our journey through the KBC Void, it's important to acknowledge the boundaries of our knowledge. Despite decades of research and remarkable advances in observational cosmology, significant uncertainties remain about the void, about our cosmic neighbourhood, and about the universe's large-scale structure. Recognizing what we don't know is as important as celebrating what we do know. The most fundamental uncertainty concerns the void's very existence. While multiple studies support the presence of a significant local underdensity, the exact size, depth, and boundaries remain debated. Different galaxy surveys and different analysis methods give somewhat different results. Some studies find a void approaching 1 billion light-years across. Others suggest something more modest, perhaps 600 or 700 million light-years. The depth varies similarly, with estimates ranging from 20 to 40% under density depending on methodology and data used. Part of this uncertainty comes from observational limitations. Galaxy surveys, even the most comprehensive ones, have gaps in sky coverage and limitations in depth. Some regions of the sky are obscured by our own galaxy's dust and stars, making it difficult to see distant galaxies in those directions. Surveys in different wavelengths of light, optical versus infrared for example, detect different populations of galaxies, potentially giving different pictures of structure. And measuring galaxy distances precisely remains challenging, especially for faint galaxies at the limits of current surveys. There's also ambiguity in defining what constitutes the void's boundary. Density doesn't transition sharply from underdense to average, but changes gradually over a considerable distance. Deciding where to draw the line between underscore quote underscore 2, underscore and underscore quote underscore 3, underscore involves some subjective judgment. Different researchers might choose different density thresholds, leading to different estimates of the void size even when using the same underlying data. Another unknown concerns the void's precise density profile. We need to know not just the average underdensity, but how density varies with distance from the centre in all directions. Is the void symmetric or lopsided? Is it more underdense in some directions than others? Does the density vary smoothly, or are there substructures? Smaller voids and filaments within the larger underdense region? Current data provides only rough answers to these questions. Better surveys will refine our understanding. But perfect knowledge may remain elusive. Questions also remain about what it means to live in such a structure. Does living in a void have observable consequences beyond the potential effect on the Hubble constant? Does it influence the cosmic microwave background in detectable ways? Does it affect the abundance of certain types of galaxies in our neighbourhood? These questions are being explored, but definitive answers remain elusive. Perhaps most fundamentally, we don't know whether the void's apparent properties are real or partially illusory. Could observational biases or selection effects make our neighbourhood appear more underdense than it truly is? Could there be systematic errors in how we measure galaxy distances, or count galaxies that create the impression of a void where a smaller underdensity actually exists? While researchers work hard to account for such issues, the possibility of subtle unrecognised errors always remains. These unknowns shouldn't discourage us. They represent opportunities for discovery, questions driving ongoing research. Science advances by identifying what we don't know and then devising ways to find out. The uncertainty surrounding the KBC Void makes it an active area of research, attracting observational programs and theoretical investigations. Over the next decade, many of these questions will likely be resolved as better data becomes available. What's important is maintaining appropriate skepticism and openness. We should take the evidence for the void seriously, without claiming absolute certainty. We should continue testing the hypothesis rigorously, welcoming both confirmatory and contradictory findings, and we should remember that even if some details turn out to be wrong, the general picture of living in an underdense region is well supported and has transformed our understanding of our cosmic neighbourhood. The boundaries of knowledge are where science happens, where hypotheses meet data, where theories are tested and refined. Standing at those boundaries, acknowledging what remains unknown, is not a sign of weakness but of intellectual honesty and scientific rigour. And it's from this position of informed uncertainty that the most exciting discoveries often emerge. Beyond the scientific questions about the KBC Void lie deeper philosophical considerations about what it means to find ourselves in such a place. These questions touch on long-standing debates about humanity's place in the cosmos and the role of chance versus necessity in determining our observations and existence. The question of whether we should be surprised to live in a large void connects to what philosophers call the anthropic principle. In its weak form, this principle simply states that our observations of the universe must be compatible with our existence as observers. We couldn't observe a universe where stars don't form, or where heavy elements don't exist because we're made of heavy elements synthesized in stars. Our very existence selects for certain properties in the universe we observe. Applied to the KBC Void, the weak anthropic principle might suggest that living in such a region isn't surprising if void environments are somehow more conducive to the development of complex life and civilizations. Perhaps the relative stability of void galaxies, free from frequent disruptive interactions, provides better conditions for the long, gradual evolution of life. Or perhaps the lower background radiation levels in voids reduce mutation rates, affecting biological evolution. These possibilities are speculative, but they illustrate how the anthropic principle could potentially explain our location without invoking pure chance. However, there's no strong evidence that voids are particularly favourable for life compared to denser environments. Life's requirements, liquid water and stable energy sources and sufficient time for evolution can be met in various cosmic environments. Galaxies and clusters, in filaments and in voids, all contain potentially habitable planets. Without compelling reasons to think voids are special for life, the anthropic explanation doesn't obviously apply. This brings us to the question of cosmic selection and observation selection effects. Throughout the universe, countless observers on countless planets look out at their cosmic neighbourhoods. Each sees a unique arrangement of nearby galaxies, a particular local environment. Some live in dense clusters, others in filaments, others in voids. We happen to be among those in a void. Is this surprising? From one perspective, no. Someone has to live in each environment, and we're simply among those who find themselves in an underdense region. Our location is no more surprising than any other specific arrangement would be. From another perspective, yes. If large voids occupy only a small fraction of space and contain only a small fraction of galaxies, then finding ourselves in one of the largest voids is statistically unlikely, raising questions about whether we're interpreting our observations correctly. This tension between accepting our location and questioning its likelihood reflects a deeper challenge in cosmology. We have only one observable universe and one location within it. We can't run experiments where we randomly sample different cosmic locations to see what's typical. We're stuck with the view from here trying to determine whether what we see is representative or unusual. This problem, sometimes called the problem of cosmic variance, affects many areas of cosmology. Philosophically, the question also touches on the nature of scientific explanation. When we encounter an unlikely situation, we have several options. We can accept it as a random occurrence, acknowledging that unlikely things happen sometimes. We can search for a reason why the situation isn't as unlikely as it seems, perhaps through anthropic arguments or selection effects. Or we can question our interpretation, wondering if what appears unlikely is actually more probable than we think due to errors or misunderstandings. From a broader perspective, contemplating our location in a void connects to age-old questions about humanity's cosmic significance. Are we central, peripheral, or irrelevant to the universe's grand scheme? The KBC Void doesn't answer these questions definitively, but it adds another layer. We're not at the universe's centre, which doesn't exist in modern cosmology. We're not even in a particularly dense, active region of the cosmic web. We're in a comparatively quiet, empty corner, a backwater in the grand cosmic city. Yet from this quiet corner, we've reached out to understand the entire cosmos, measuring distances to galaxies billions of light years away, probing the universe's first moments and mapping its larger structures. Our peripheral location hasn't limited our ability to comprehend the whole. If anything, our relative isolation has given us a clearer view, free from the confusion of too many nearby neighbours. There's a kind of poetry in this, significance arising not from central location but from the act of understanding itself. These philosophical reflections don't resolve scientific questions about the void, but they enrich our appreciation of what those questions mean. Science and philosophy intertwine when we contemplate our place in the cosmos, each informing the other, together creating a fuller picture of our cosmic situation and its implications for how we understand ourselves. As our journey approaches its end, let's turn our attention to the aesthetic dimension of cosmic structure, to the remarkable beauty of the cosmic web and the voids within it. Science often focuses on measurements and predictions, but there's also wonder to be found in simply contemplating the structures the universe creates. The cosmic web, viewed in 3 dimensions through galaxy surveys, is breathtaking in its complexity and scale. Imagine visualizing millions of galaxies, each represented as a point of light, arranged in space according to their actual positions. What emerges is a delicate tracery of filaments and walls, glowing threads connecting bright nodes where clusters shine, all surrounding darker voids like chambers in a vast palace. The structure resembles neural networks in the brain, or mycelium spreading through soil, or frost patterns on a window, nature's tendency to create similar forms at vastly different scales. The filaments themselves are elegant in their slenderness. They can stretch hundreds of millions of light years in length, but measure only tens of millions of light years across. Like cables in a suspension bridge, they connect massive structures while spanning great emptiness. Along these filaments, galaxies flow like traffic on a highway, following the gravitational potential wells created by dark matter's distribution. The filaments glow with the collective light of billions of stars in thousands of galaxies, rivers of light crossing the cosmic darkness. The voids contribute to this beauty through contrast. Without the emptiness, the bright filaments wouldn't stand out. The cosmic web's aesthetic power comes partly from the interplay of light and dark, density and emptiness, structure and void. The voids provide the negative space that makes the positive space visible, like the silence between notes that makes music coherent rather than noise. This aesthetic dimension of cosmology reminds us that science isn't purely instrumental or utilitarian. We don't study the universe only to gain practical benefits or to make predictions. We study it partly because it's beautiful, because understanding and observing cosmic structure satisfies something fundamental in human nature. The KBC Void and the cosmic web it's part of are worth studying for their own sake, as manifestations of nature's capacity to create beauty at the largest scales. Photography and visualization have made this beauty accessible to wider audiences. Images from telescopes and simulations appear in books, museums, and online, allowing people to see the cosmic structures astronomers study. These images inspire wonder and curiosity, connecting people to the cosmos in emotional ways that complement scientific understanding. A child seeing an image of the cosmic web might be moved to study astronomy, beginning a journey that leads to deeper understanding. As we contemplate the beauty of our cosmic neighbourhood, the void we inhabit and the web it's part of, we can appreciate that we're not just analysing data or testing hypotheses. We're engaging with one of the universe's most remarkable features, a structure so vast and intricate that it challenges comprehension, while simultaneously inviting contemplation. The cosmic web is beautiful, and recognising that beauty enriches our experience of studying it. There's also beauty in the human endeavour itself, in the fact that beings on a small planet have mapped structures billions of light years across, have understood the physics governing them, have placed themselves accurately within this grand architecture. Our capacity for understanding, for reaching beyond immediate experience to grasp the universe's larger structures, is itself a kind of beauty, a manifestation of consciousness engaging with cosmos. As we near the end of our exploration, it's worth reflecting on what the KBC Void and the broader study of voids teaches us about cosmology, about scientific methodology, and about our relationship with the universe. These lessons extend beyond the specific facts about our cosmic neighbourhood to more general insights about how we understand the cosmos. First, the void teaches us about the importance of large-scale surveys. Without comprehensive mapping of galaxy positions across billions of light years, we would never have discovered that we live in an underdense region. The void's existence emerged from painstaking accumulation of data, from measuring the redshifts of hundreds of thousands of galaxies and analysing their spatial distribution. This reminds us that progress in cosmology often requires vast observational programs, sustained over decades, collecting data whose full significance might not be apparent until analysed comprehensively. The collaborative nature of this work is also instructive. No single astronomer or institution could conduct surveys of the required scale. Teams of researchers, observatories around the world, and public databases accessible to all scientists have all contributed to mapping our cosmic neighbourhood. The KBC Void was discovered through analysis of publicly available survey data, demonstrating how open science and data sharing accelerate discovery. This collaborative model represents science at its best, pooling resources and expertise to address questions too large for any individual or group to tackle alone. The Void also teaches about the value of questioning assumptions. For decades, cosmologists assumed our local region was roughly average in density, an assumption consistent with the cosmological principle. The discovery that we might live in a significant underdensity challenged this assumption, forcing reconsideration of how we interpret local measurements. This illustrates a crucial scientific principle. We must always test our assumptions and remain open to the possibility that what we've taken for granted might be wrong. There's a lesson here about the relationship between local and global measurements. In cosmology, we often extrapolate from local observations to universal conclusions. We measure the Hubble constant locally and assume it represents the universal expansion rate. We observe nearby galaxies and assume they're representative of galaxies everywhere. The Void hypothesis suggests we need to be more careful about such extrapolations. Local conditions might differ from cosmic averages in ways that affect our measurements. This doesn't mean local measurements are useless, but it means we must be thoughtful about what they represent. The Void teaches us about statistical reasoning in cosmology. When we encounter an apparently unusual observation, we must carefully assess its significance. Is it genuinely rare, or does it only appear rare because we're applying the wrong statistics? Are there selection effects making certain outcomes more likely to be observed than their cosmic frequency would suggest? These questions require sophisticated statistical analysis and careful thought about observation selection. The Void's possible rarity has sparked detailed statistical investigations, improving our methods for assessing significance in cosmological observations. Another lesson concerns the interplay between observation and theory. The Void's potential to explain the Hubble tension emerged from theoretical work exploring how underdensities affect expansion measurements. Observers then sought to test these predictions, measuring the Void's properties more precisely. Theory and observation work together iteratively, each informing and guiding the other. This partnership is fundamental to how cosmology progresses, with theoretical predictions suggesting what to look for and observations testing those predictions and suggesting new theoretical questions. The Void also teaches humility. If we do live in an unusual location, it means our observations might not be as representative as we thought. We're not viewing the universe from a typical vantage point, but from a somewhat special one. This requires humility in how we make cosmological claims, acknowledging that our perspective is limited and potentially biased. It's a reminder that while we've learned an enormous amount about the universe, significant uncertainties remain, and our current understanding might require revision as more data becomes available. There's a lesson about the importance of multiple independent tests. No single observation definitively proves or disproves the Void hypothesis. Instead, multiple lines of evidence, galaxy surveys, peculiar velocity measurements, ISW signals, supernovae observations must all be brought to bear. When multiple independent methods converge on the same conclusion, confidence grows. When they disagree, we know more work is needed. This multi-pronged approach to testing hypotheses is essential in cosmology, where we can't run controlled experiments. The void teaches about the value of patience in science. The discovery and characterization of our local underdensity has taken decades and remains ongoing. Quick answers to deep questions are rare. Progress comes through sustained effort, gradual accumulation of data, and patient analysis. Researchers who began studying local cosmic structure in the 1980s are seeing their work mature into detailed characterizations of the KBC Void today. This long timescale reminds us that important scientific questions often require career-long commitment. From a broader perspective, the void teaches us about the universe's diversity and complexity. The cosmos is not a simple, uniform expanse, but a rich tapestry of structures at all scales. Voids, filaments, clusters, superclusters, each contributes to this diversity. Understanding the universe requires appreciating this complexity, not seeking to reduce everything to simple averages. The richness of cosmic structure is what makes cosmology endlessly fascinating. Finally, studying the void teaches us about the human capacity for understanding. From our small planet, using instruments we've built and theories we've developed, we've mapped structures 1 billion light-years across and understood the physical processes that formed them. We've placed ourselves accurately within this vast cosmic architecture and are working to understand how our location affects what we observe. This achievement reflects millennia of accumulated knowledge, the work of countless scientists, and the power of the scientific method to reveal truths about nature far beyond immediate human experience. These lessons, drawn from studying one large cosmic void, apply broadly to how we do cosmology and how we understand our place in the universe. They remind us that science is a process, ongoing and self-correcting, built on collaboration, data, careful reasoning, and willingness to question even our most cherished assumptions. And they show that even our cosmic address, the particular void we call home, has much to teach us if we approach it with curiosity and rigour. We've travelled far together through the KBC Void, exploring its discovery, its properties, its implications for cosmology, and its place in the cosmic web. Now, as our journey nears its end, let's contemplate what it means to accept that we live in such a place, to embrace the emptiness that characterises our cosmic neighbourhood. Emptiness in everyday language often carries negative connotations. Empty implies lacking, insufficient, devoid of value or interest. But in cosmology, emptiness is neither good nor bad. It's simply a property, a characteristic of the space we inhabit. The KBC Void isn't empty in an absolute sense. It contains our galaxy and thousands of others. It contains dark matter and dark energy. It's permeated by cosmic rays and ancient light from the Big Bang. It's empty only relative to denser regions, only in the sense that it has less matter than average for a comparable volume of space. Accepting this emptiness means acknowledging that our cosmic environment is different from what we might have expected. If you imagine the universe as uniformly filled with galaxies, you'd be surprised to learn that most of space, including where we live, contains far fewer galaxies than the richest regions. But this surprise fades as understanding grows. The cosmic web structure, with its voids and filaments, is natural and inevitable given how gravity shapes matter distributions. We shouldn't expect uniformity because the physics doesn't produce uniformity. There's a kind of peace in accepting our location. We don't need to wish we were elsewhere, in a dense cluster surrounded by bright neighbours. Our void is our home, the environment that shaped our galaxy's evolution, and perhaps made possible the stable conditions that allowed our solar system to form. If the stability of void environments contributes to life's development, then we owe our existence partly to the emptiness around us. In this sense, the void isn't a cosmic shortcoming, but a cosmic gift. Acceptance also means integrating this knowledge into how we understand ourselves. Our cosmic address is part of our identity as inhabitants of Earth. Just as we identify as residents of a particular country or city, we can identify as residents of the Milky Way galaxy in the local group within the KBC Void. This expanded sense of place connects us to structures far larger than ourselves, grounding our existence in the vast cosmic context. The emptiness of our neighbourhood might also encourage contemplation of what absence and presence mean. In a void, we appreciate the galaxies we can see more fully because they're relatively rare and isolated. Each galaxy is distinct, not lost in a crowd. Similarly, the darkness of space between stars and galaxies isn't merely absence, but a canvas that makes the light visible. Without darkness, we couldn't see stars. Without voids, we couldn't perceive the cosmic web structure. This connects to deeper questions about meaning and significance. Does living in a void make us less significant cosmically? Only if we equate significance with being in a crowded, active location. But significance might come from other sources, from the complexity of life, from consciousness capable of understanding the universe, from the very fact of existence in a cosmos governed by comprehensible laws. These don't depend on living in a dense cluster. They're equally present in a void. Accepting emptiness also means accepting uncertainty. We don't know everything about the void. Its exact properties remain somewhat uncertain, and its impact on cosmology continues to be investigated. Rather than finding this uncertainty troubling, we can embrace it as an invitation to keep exploring, to remain curious and engaged. The incompleteness of our knowledge makes the journey more interesting, the discovery more rewarding when it comes. There's also acceptance of change. The void is evolving, growing larger and emptier as cosmic time passes. In the far future, it will be even more empty than today. This evolution is part of the universe's story, the natural progression from the nearly uniform early cosmos to the highly structured present, and eventually to an even more dispersed future. Accepting this change means recognizing that the universe is dynamic, not static, and that our moment in cosmic history is one point in a long evolutionary arc. From a philosophical perspective, accepting emptiness might teach us about the nature of reality itself. The void is mostly space, mostly distance between concentrations of matter. This reminds us that the universe is largely empty, that matter is the exception rather than the rule. Even atoms are mostly empty space, with tiny nuclei and electrons separated by distances enormous compared to their sizes. Emptiness is fundamental to nature at all scales. Yet within this emptiness, extraordinary things happen. Stars form, planets coalesce, life arises, consciousness develops. The emptiness provides the stage on which complexity plays out. Without space, without separation, there could be no distinct objects, no motion, no evolution. Emptiness enables existence as much as matter does. As we prepare to conclude our journey, consider this. Living in a cosmic void is not a cosmic misfortune or accident. It's our home, the place from which we observe and understand the universe. The void has given us a relatively clear view of distant structures, a quieter environment for galaxy evolution, and possibly a stable context for life's development. It's made us questioners and explorers, seeking to understand why our neighbourhood is as it is. The acceptance of emptiness, then, is the acceptance of our actual situation, rather than some imagined ideal. It's recognising that where we are is exactly where we should be because it's where we are, and that this location offers its own unique perspective and opportunities. The void is vast, yes. It's relatively empty, certainly. But it's ours, and understanding it has revealed as much about the universe as studying any denser region could. As we allow this acceptance to settle, we can appreciate the journey we've taken together. From the initial revelation that we live in a void, through the exploration of what that means scientifically and philosophically, to this moment of contemplative acceptance, we've travelled not just through space, but through understanding. And in that journey, the void has become less strange and more familiar, less empty and more full of meaning. The void is our home, and perhaps that's enough. We've travelled together for 2.5 hours, drifting slowly through the largest void in our cosmic neighbourhood, perhaps one of the largest voids in the entire observable universe. Thank you for staying with me on this journey, for letting these ideas and images wash over you as the night has deepened around you. It's been a privilege to share this exploration of our cosmic address. From the initial discovery of the KBC Void through galaxy surveys and statistical analysis, we moved to understand what voids are and how they form. We explored the Hubble tension and how our residence in a void might explain this cosmological mystery. We mapped the cosmic web structure, considered dark matter's hidden role and dark energy's influence, and contemplated the evolution of voids across cosmic time. We examined the largest voids known beyond our own, reflected on the philosophical questions our location raises, and appreciated the beauty of cosmic structure at the larger scales. The answer to the question that's threaded through our entire conversation, whether we truly live in a giant cosmic void and what that means, can be given with reasonable confidence now. Yes, the evidence suggests we do live in a significantly underdense region of space, one extending perhaps 600 million to 1 billion light-years across. Whether this void fully explains the Hubble tension. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. Whether this void fully explains the Hubble tension or solves other cosmological puzzles remains to be determined. But the void itself appears real, a natural feature of the cosmic web and our cosmic home. Perhaps the deepest answer is that the void has taught us to question our assumptions about being typical, to recognise that our observations reflect our local environment as much as universal properties, and to appreciate that even an unusually empty corner of the universe offers its own gifts, a clear view outward, stable conditions, and a unique vantage point for understanding the cosmos entire. If you enjoyed this slow drift through cosmic emptiness and structure, a like and subscribe helps others discover these peaceful explorations of the universe. And thank you, truly, to those who return week after week to these contemplative journeys through space and time. Your presence here makes this work meaningful. Wherever you are in the world right now, whether you're looking up at stars through a window or lying in darkness with only these words and images in your mind, I hope your breathing has slowed. I hope your thoughts have quieted and organised themselves around these cosmic contemplations. I hope your body feels heavy and warm and ready for rest. You've spent these hours learning about structures billions of light years across, about voids and filaments and the grand cosmic web, about our place within it all. Look up at the darkness between the stars if you can, or imagine it if you cannot. That darkness, that emptiness extends around our galaxy in all directions for hundreds of millions of light years. It's the void, our void, the KBC Void, and in that vast emptiness float scattered galaxies like islands in an ocean, each one a system of billions of stars, each star potentially hosting planets, each planet a world of its own, all of it floating in the cosmic foam, in the structure that emerged from the universe's first moments and continues evolving toward an increasingly empty future. There's no centre to the void, no special place that defines it, but if there were, we might be close to it, drifting near the deepest part of the underdensity, the place where galaxy density falls lowest. From here, we've looked outward and seen the universe not as we imagined it might be, but as it actually is, beautiful, structured, diverse, and in our neighbourhood at least, remarkably spacious. What we're left with is not an answer to every question, but a better question. a more refined understanding. We've moved from do we live in a void to how large is our void and how does it affect what we observe. We've moved from confusion about conflicting measurements to potential explanations grounded in our cosmic location. We've moved from assuming we're average to accepting we might be somewhat special, and recognizing that this specialness doesn't diminish the universe or our place in it, but enriches both. Sleep well tonight, wherever you are in the cosmic void that is our home. Dream, if you dream at all, of vast dark spaces punctuated by light, of filaments connecting clusters across gulfs of emptiness, of our small planet orbiting its ordinary star in the outer reaches of a spiral galaxy that itself drifts through the underpopulated regions of cosmic structure. Dream of the cosmic web in all its glory and know that we are part of it, inhabitants of its spacious chambers, observers of its grand architecture. We live inside a cosmic void, and no one told us for billions of years, but now we know. Now we can look at the night sky with new understanding, can recognize the significance of the darkness between stars, can appreciate our location in the universe's vast structure. This knowledge changes nothing about our daily lives, but it changes everything about how we understand our place in the cosmos. And perhaps that's what matters most. Not where we are, but that we've come to understand it, that we've mapped our cosmic address with increasing precision, that we've connected our small corner of existence to the universe entire. Good night. Rest well in the emptiness. Let the darkness of space mirror the darkness behind your eyes as sleep takes you. And know that tomorrow, when you wake, you'll wake in the same cosmic void you've always inhabited, but now you'll know it, recognize it, and perhaps appreciate it in a new way. The void is our home, and understanding it has brought us home to ourselves. Good night.